Thank you very much. So today I'll be speaking about some nice lattice paths, some relationships, some bijective relationships between them. And this is based on joint work with André Azanovsky and Sylvie Bantrouillet, as well as joint work with André Azanovsky and Daniel Broche. Great, so let's get started. Hopefully this is going to be given at a level that everybody at this stage in the week is easy to follow. I know everyone has different backgrounds, so we're going to go through things on quite a general level. So we're going to start with patterns in lattice paths via automata. So review some of the background, then we'll get into walks in the quarter plane, or patterns in walks in the quarter plane, and then look at a fun model of lattice path which has a moving boundary. Right, so in this community I probably don't need to say or motivate why we care about studying patterns in lattice paths or combinatorial objects. But in general, we study patterns in various different types of combinatorial objects, and typically we ask what is the number of structures of a given size which have a certain number of patterns occurring in them. Right, so if we look, for example, at Dyke paths, we have some pattern we want to study. In this case, the pattern is up, down, up. We can get a bivariate generating function which represents this. So as we've highlighted there, the term where we have paths of length 8, Z marks the length, V marks the occurrence of patterns. This represents here, we accidentally have a U instead of a V, but this represents over here all of the terms of the sequence. So we have 1 which has 3 occurrences of that pattern, we have 3 which has 2 occurrences of that pattern, and we have 6 which have 1 occurrence of the pattern. And in general, if we gave this to undergraduate combinatorics students, we would be able to they would then be able to solve this type of problem by busy doing a nice ad hoc method. So we have Dyke walks, we have a standard symbolic decomposition for Dyke walks. What we can do is we can follow the pattern in this decomposition. So if we look at the walks, we can have, we can have empty, or else we can have, and to create our pattern up, down, up, we can have this Dyke path here is empty. So we have up, down, and then we have to start with an up. So this one cannot be empty, which gives us our first term. Both of them being empty gives us our second term, and then this one not being empty gives us our third term. And then ultimately from this, using V to mark that the pattern has occurred, we can get some functional equation for these generating functions. And then once we have this functional equation, we can then determine things like the normal generating function for these paths, the generating function where we are avoiding some pattern, and then the generating function for the total number of patterns occurring in a given length to get stuff like the average. Okay, so this is very nice, very simple, but how are we going to do it if we now have some arbitrary step set? And if we, let's say, have like even 5 very strange steps, suddenly finding a symbolic decomposition is not so fun and not very easy. And so it would be nice to have some less than ad hoc or more than ad hoc. In which direction do we want the ad hoc? In any case, a general method to study patterns in these lattice paths. And this general method comes out of automata. So again, carrying on with the theme of up, down, up, or up, down, up, what we do, reminding ourselves of automata from yesterday, we already saw definitions, but we have a set of states, which in this case we have these states over here, the circles. We have an alphabet. In this case, our alphabet is up and down. We have transitions. In this case, it's a transition function. So there's a unique transition for each element of the alphabet from each state. And then we have an initial state, so the place that we're busy starting. And then usually we have final states or accepting states, which are usually marked by some sort of double circle. But in this case, they are all final states, and I neglected to then mark that they were final states. But that's essentially the setup of an automaton. And in order to follow the patterns that are occurring in our lattice path, we interpret our Dyke path now as a word. We feed that word through our automaton, busy following which state it is in at each point in time. And when an up, down, up occurs, we get to the state up, down, up. We mark the transition with the final up that occurs. And then in this way, we can count, well, we can model whenever this up, down, up occurs. So just for the purposes of fitting nicely onto the slide, this automaton here with 4 states is equivalent to this automaton here with 3 states. So we're going to use this in future to represent marking or locating the up, down, ups. Okay, so now we have that. What can we do with that? Well, as many of you are probably familiar with, we can treat this as a walk on a graph. We get an adjacency matrix. The adjacency matrix, what we're going to do is we use Z to mark length. For now, we don't have any Z in our adjacency matrix. We use U to mark height, and we use V to mark our pattern. So what we're going to do is, imagining the states are numbered 1, 2, and 3, we form our adjacency matrix, and of course, whenever we have the red transition being taken, we have a V, and then in this case, it's an up step, so a U. So we have an adjacency matrix now, which represents what's happening in our directed graph or our automaton. And then if we want to formulate or form a generating function, well, almost a generating function at this point, what we have here is summing these all up. So if we want a walk of length 1, we have Z times A, walk of length 2, ZA squared, and so on. Then each corresponding entry, Aij, in our matrix is going to be the number of walks from starting in state I and ending in state J. Okay? And so in order to then take into account the fact that we have an initial state, which is where we're allowed to always start, and in this case, all of our states are final states, we take initial vector, multiply it in, representing the first one being our initial state, and our final vector here, where we represent which ones are allowed to be final states. And in this case, we can then quite easily work out what the inverse of a matrix is, multiply it out, and we can get a generating function. However, at this point, what you probably are thinking to yourself is, okay, that's very nice, but at no point have we handled any non-negativity constraints, okay? So this is very nice for getting unconstrained Dyke path or Dyke walk. But now what we want to do is we want to now add in this non-negativity. So what we do with this is we use a push-down automaton. So what this is just a normal automaton, but we attach a stack to it. Now, for our intents and purposes, what we're essentially doing is keeping track of the height above the x-axis at all times. And so it's not a very complicated stack. We can just use a single letter of the alphabet on our stack to keep count, okay? So what we're going to do is, when we're busy now reading this word that we're considering, whenever we read an up, we're going to push a U onto our stack. And whenever we read a down, we're going to pop a U from our stack. Okay, so let's just do a quick example. So we read a U, we push onto the stack, we push onto the stack, now we pop, we push, pop, pop, push, pop, push. Okay, so that's more or less how these push-down automaton work. And what we can do now with our generating functions, or to obtain generating functions from our adjacency matrix, is we can now do something which is known as the vectorial kernel method. I'm not going to go into any details about how the vectorial kernel method works, but essentially just to point you in this direction. So just like the kernel method, which you would have seen here, showed us some kernel method the other day, what we're going to do is we're going to essentially simulate busy adding a step to our paths, and then we're going to remove any of the illegal steps, so the steps that are going below the x-axis. And so this results in some form over here, which then there are methods that you can do or try to do in order to get the generating function out. Okay, so to just summarize these methods, so we have a method for busy working out while studying patterns in unconstrained walks. We have a method for busy studying patterns in constrained walks, which are sort of one-dimensional above the x-axis. And what can this tell us about the generating functions? So when we have just the automaton which doesn't have a stack, what we can say then is that the generating function is a rational generating function that comes out. You can see this quite easily with the matrix calculations. And then with the push-down automaton, and we must be careful not all push-down automata, but rather for a subclass of push-down automaton, very specifically the ones that encode unambiguous context-free grammars or context-free languages. We don't really go into languages too much now, but those ones then give us an algebraic generating function. So ultimately, if you can encode combinatorial objects in this way, you can know what type of generating function they're going to have. Good, so maybe just to point out some other things that we're not going to get into, but there's also some work towards classifying the languages and automata which encode definite generating functions. So in particular, shuffles of context-free languages, so using shuffle with one letter to sort of point, was done by Mishna and Zabrocki in 2008. And then in addition, two-way reversal bounded counter machines. And maybe just to quickly say what a two-way reversal bounded machine is, just so that we have a little bit of an idea of what that is. I think it's not necessarily an extremely common notion. Is if we pretend we have a word, now I'm going to draw the word a bit like a stack, but yes, maybe our two-way machines, so currently what we've seen so far, we've read our input from left to right, we've processed it in our machine, and we've seen if it's in an accepting state, okay? With a two-way machine, what we do is we are now allowed to not just move from left to right, but we're allowed to move backwards and forwards as well. So each time that we are in a state, we read an input, we get then told if we move left or right in our tape, okay? So that's what a two-way automaton is. A counter machine, we're again having these stacks to keep, a stack to keep track of the height. And then reversal bounded essentially means we're not allowed to move back and forth too many times. So there's a bound, upper bound to the number of reversals we can do, and similarly, the number of times we can pop off of the stack. Okay, good. So now we have understanding more or less of what's going on the automata front. Now we're going to head into looking at some patterns in the quarter plane. So one-dimensional walks, things seem reasonably manageable, but in general, two-dimensional walks, things become incredibly hard, as I'm sure many of us are aware. So just in case anybody's never seen it before, I like to do this. Crevras walks, we have a northeast step, we have a south step, and we have a west step. And these are enumerated staying inside the quarter plane. These are enumerated by this formula, which combinatorially is very exciting and looks very simple. So if you saw this for the first time, at least when I saw this for the first time, I was very excited. I thought, okay, cool, well, we have sort of ternary trees going on there. We could add some sort of coloring. We could maybe find some equivalence class. Then we have a very nice, simple bijective proof, right? Wrong. So ultimately, there's no extremely nice, simple bijective proof for Crevras walks, as many of you are aware. And this is something that maybe, well, we will not get really any closer to it today, but studying patterns in walks in the quarter plane, particularly Crevras walks, perhaps there's some potential to follow some patterns, to find some matching statistics and so on, find some nice bijections. So that's something to sort of look out for what's coming. So in case you have never seen this before, essentially crevasse walks were introduced in Crevasse's thesis in 1965. And then people continued to work on them, improving the proofs, Crevasse and Niederhausen, and in Niederhausen. In all of these approaches up until 2005, they were more or less guess and prove approaches. And the first direct derivation of the proof of the Crevasse enumeration was by Bousquet-Milou with a multivariable kernel method. And then in 2007, there was a bijection. It's not with the simplest objects like ternary trees, which are nicely colored and so on, but still a very nice bijection, but some sort of proof from the book bijection is still outstanding. Okay, so, I neglected to mention, but at some point, the algebraicity of Crevasse walks was proven. And so we have this question, Crevasse walks are algebraic, so perhaps we can study patterns in Crevasse walks by busy looking at, again, a push-down automaton, okay? But if we let me go a little bit more with language theory, if we have a language which is context-free, meaning that if we have a language which is represented or recognized by a push-down automaton, then there's something called the pumping lemma, which you can use to show that a language is not part of this context-free family. And so essentially there's some pumping length P, where if you have a word that is larger than this pumping length P, you can write it in this way, and then the following things apply. And in particular, what we want to use is that if we can write it in this way, such that these two hold, we need to check that this word has to then also be in the language, okay? And if we can find a word that these two things hold, but this does not hold, we can say then it's not context-free, so it can't be represented by a push-down automaton. And with Crevasse, it's quite easy to see this. What we can do is we can set or take the word, the diagonal northeast step to the P, a down step to the P, a west step to the P, and we can then see that any choice of our V, Z, and X, so the center, the part that's going to be pumped, is now not going to be possible to be having the same numbers of A's, B's, and C's in the resulting word. And so this cannot be represented by a context-free language, and so we don't really have an approach with push-down automata. Okay, so how can we really approach studying patterns in Crevasse walks? We previously said that Mireille Bousquet-Milou derived some sort of multivariate kernel method for studying Crevasse walks. And I mean, this took 40 years, I guess, to come into play. So do we think that maybe some multivariate kernel method might be able to study patterns in walks in the quarter plane? Well, at the moment, as far as I'm aware, nothing like this has been developed. But there's a very nice, naive approach that we could do. So we could just do some computer experiments, yeah? So we have Crevasse walks, we choose some pattern, we forbid this pattern, and we count how many of these occur. So let's just choose an arbitrary pattern, west-west, and we count how many of these occur, and the sequence, as we start to count, is looking a lot like Gessel excursions, okay? So for those of you who don't know, Gessel excursions are another type of walk in the quarter plane. It's another algebraic model. It's also it's been quite a popular one. There were difficulties in trying to prove that it was algebraic. So out we get Gessel excursions, which look like this, which indicates perhaps we should just try to find a bijection between Crevasse walks which are avoiding west-west and Gessel excursions, which is quite exciting to somehow be able to connect the two famous walk in the quarter plane models. And the bijection actually turns out to be incredibly simple. So we call it the shortcut bijection. As you can see, basically, if you could do north, east, west, you just go up instead, so you always are just taking a shortcut. and the other ones stay the same. So you can see from this, if you look at all of the 9 possible pairs, everything would stay the same except for the ones which sort of have a waist in them, and if there's a waist in them, the thing that comes before the waist has to then be one of the other types of steps, which we then take a shortcut with. Okay, so extremely simple relationship between crevasse walks and Gesell walks. Good. What else can we find? So now we avoid the pattern west-northeast, and again, Gesell excursions. Okay? Are they all just related to Gesell excursions? Are crevasse walks just Gesell excursions? No. But for now, so west-northeast is Gesell excursions, west-west is Gesell excursions. And so what we are interested in is seeing, are these parameters equally distributed? So yes, if we take k west-west steps in one and L west-northeast steps, this is then going to be equal to L west-west and k west-northeast. And there's a nice simple bijection again. All the bijections are reasonably nice and simple. So we have, for each west-west, what we have to do is the first west of the west-west, we mark it, okay? And the northeast of the west-northeast, we mark that, okay? We note their local indices. So by local index, I mean that we look at, for example, all of the west steps, and we count them in order 1, 2, 3, 4, 5, 6. And similarly, the local indices of the northeast ones. So in this case, we have 3 and 6, and the local indices of the marked west ones, 1, 4, and 5. Okay? Then, what we do, so I increasing from 1 to k, we take the west step that's marked, and we insert it immediately before the northeast step, which has the next index, so the index plus 1, shifted by 1. So in this case over here, for example, we have the step, the west step with index 1. We place it before the northeast step with index 2. And you can check to yourself if this is possible. So we're always going to move an index with a lower number in front of one with a higher number, so it will still result in a valid path. Okay, so performing that procedure, we then get this path. Now we have introduced some west-northeast steps, but in this case, what we can do, well, we ignore the west-northeast steps which have not been marked. So we're keeping our marked northeast steps. Okay. We now, again, we have our local indices, and we're going to go from back to front now, so from the end to the start. We remove the west step that's just before it, and then we insert it before the other west step with the exact same index. So in this case, we have this west step gets put before the sixth one. This west step gets put before the third one because it corresponds to the indices. And in this way, what we've done, hopefully it is correct at this point, we have one west northeast, we have another west northeast, so we now have 3 west northeasts and 2 west wests. So in this way, basically applying these steps, we're able to shift between our 2 statistics, and it's an involution, so if you apply it twice, you're going to get the same path back again. Good. So now what about the other patterns? Well, just looking at patterns of length 2 up until symmetries in crevasse walks, it's actually a little bit surprising that nothing awful truly happens. So we've already discussed west-west, west-northeast, and these results in Gesell excursions. Northeast-west, we get Gesell excursions which end with a down step. And then northeast-northeast, polio excursions, south-west, diagonal excursions. The definitions or the step sets for these are given here. They're all existing in the quarter plane. And so now we ask, is it a coincidence? So what's actually happening here that we have all these strange relationships between walks in the quarter plane? And the answer is, you tell me. So ultimately, there's no real explanation for why this should occur, that we have these nice relationships. If you start to look at longer step patterns, at least if you search the OEIS, you're not getting any other famous walk patterns. So somehow this is just coincidentally happening, and quite exciting actually that we have relationships between Crevasse and Gesell. Okay, so now we think about nature of generating functions. So as we discussed previously, if you have a deterministic finite automaton, you get a rational generating function that was for unconstrained walks. For the push-down automata with the constrained non-negative walks, we end up with algebraic generating functions. So it's natural to say, okay, well, with patterns, what's really happening when you're avoiding patterns with walks in the quarter plane? And in particular, you could think of it in terms of if there's some nice underlying structure, almost like an automaton. So currently walks in the quarter plane, you can think of them as automaton with 2 stacks, which is, yeah, Turing machine, maybe not so much to do counting-wise there. But what's happening is there's some underlying structure that can then tell us what type of generating function busy avoiding certain patterns is going to give us. So in the first 2 cases we have, or 3 cases rather, we have algebraic generating functions. So Gesell is known to be algebraic. Again, you could look at Gesell and you could apply the pumping lemma. You now, for Gesell, you have A to the n, B to the n, C to the n, D to the n. Pumping lemma will again show you that this is not a context-free grammar, so it can't be encoded by a push-down automaton. So we're not really simplifying from Crevasse being not context-free to getting something context-free. And then the bottom 2 models are D-finite. So we could sort of ask the question, if we have an algebraic walk and we're avoiding some pattern, maybe some restriction on the pattern, what is actually happening to the generating function? Are we consistently living in some sort of algebraic D-finite realm? Could it get worse than that? Could we go to differentially transcendental? And the answer is, yes, everything can always get worse. So maybe just to point out, as I already said verbally before, so I'll quickly go through it. We already said that there's cases where we have rational generating functions, algebraic for patterns, and now we need to find some classification for what's happening for patterns in the quarter plane. So now to the yes, it can always get worse. So there's an example. We have a model. Here we have multiplicities on our steps indicated by the numbers, but this model over here is algebraic. And if we avoid some steps in it, so technically just avoiding one step is avoiding a pattern, although maybe it would be interesting to see if avoiding longer patterns is only allowed, so greater than or equal to 2, if bad things also happen, probably. We can get a model which is differentially transcendental. So yes, it does get worse than avoiding patterns in algebraic, gives algebraic or D-finite, or even D-algebraic. Okay, good. So I often get asked when, if I show this, I often get asked, well, what about other quarter plane models? Okay, so the answer is that if you do a reasonably brief search in other quarter plane models avoiding patterns, if you search the OEIS, nothing really comes up in the OEIS, okay? But there are some, if you generate some terms and put them into some guessing software, there are other relationships, so you could conjecture that some of them are D-finite and so on. Okay, good. So classification of pattern avoidance in walks of the quarter plane. Lots needs to be done there. Hopefully people in this community are sort of interested in trying to do some sort of classification. And now, to sort of finish off, I'll show you another model of lattice paths, which is a little bit fun and experimental. So far, when most lattice path models and when studying patterns in lattice paths, you sort of just count the number of patterns and that's it. But it's sort of reasonably natural to say, well, what happens if something happening in the lattice path then triggers something changing in the future of the lattice path? And that's where this concept of a dynamic boundary comes in. So what we have is we make some set of steps, and then we have a set of patterns. And once a pattern occurs, there's some sort of condition attached to it, which then changes the boundary of the lattice path. Okay, so the boundary moves up or down depending on what has just occurred. Okay, so like in this case here, we have a standard Motzkin path, but if up, down, down occurs, we move the boundary up. That's immediately after the last step of the pattern has occurred. And if down, up occurs, then we move the boundary down. That's immediately after the last up step of down, up occurs. And then you could place various restrictions on it. So at the moment, I'm busy saying that we shift the boundary immediately after that last step. You can also change it a little bit by saying shift it before. You can also say it has to end at 0, not on the boundary line. But essentially busy playing with these types of models to see what actually happens. Okay, so with these cases, if you were paying attention to the automaton discussion at the start, this would be algebraic. So you can encode this in the automaton. You can take your pattern, make your patterns the states according to your pattern, and then at the end of your pattern, you can then use the epsilon transition, so a transition that doesn't use read any input, to then adjust your boundary accordingly. So usually you are not allowed below 0. So if you are moving your boundary down by 1, you add 1 to the automaton, so you artificially can move down again. And if you're moving down, up, you subtract from the automaton, or from the stack, sorry. Good. So these also, with some adjustments to the step set and adjustments to patterns, but it's quite a significant, a little bit of an involved process. You can sort of model these through pattern avoiding walks. And sometimes there are interesting relationships between these types of lattice paths with moving boundary and other combinatorial objects. So one such relationship I will just show you in the last bit. We have Motzkin paths, again Motzkin paths with the up, down, and level step. If we have down and level, this shifts the boundary by -2. If we have up and level, it shifts the boundary by 2. And we're just going to call the set of excursions of these Motzkin paths, which end on the boundary, things shift as the boundary changes, Mn. Okay. And then in addition, so Young tableaux seem to come up a lot when studying lattice paths, especially bounded Young tableaux. So Motzkin paths, normal Motzkin paths are related to Young tableaux, which are bounded of bounded heights less than or equal to 3. Guillaume walks are related to Young tableau heights less than or equal to 4. So these types of things start to come up a little bit. And these shifted Young tableau that we're going to look at now, essentially the ith row starts in the ith position. So we sort of have a staircase going on for the start, okay? Entries are the numbers from 1 to n, always increasing along the rows and columns. And as I mentioned, height less than or equal to 3. So this is just what one looks like. And we're going to claim that there's a bijection between these Motzkin paths with, of length n and these shifted Young tableau with n+1 entries. Okay, so there's what they look like. A bit strange looking, but oh well. Good. So we will just show the bijection or demonstrate the bijection. Whenever we have a down left, we go -2, and whenever we have an up left, we go up 2. Okay, so what we're going to do is whenever we see up left, we're going to shift, or we're going to just flip it around. So in some sense, you can also see this moving boundary as you can flip them around and things then end on the x-axis, but some restrictions sort of take place with the shifting boundary. Okay, so we have an up left. We're going to transform it to a down left. And then what we're going to do is look at all of the down lefts, which were originally down lefts, and we're going to mark, the left step associated with it. I'm saying left. It's not even moving left. Level, good, whatever. So we're going to mark the level step that's associated with it. Okay? In some cases, the level step might not be the rightmost level step in a contiguous sequence of level steps. Okay? And in this case, what we're going to do is we're going to then take one that's not the leftmost in a contiguous sequence of level steps and move it to the rightmost position, sorry. Okay, left and right is a bit difficult for me. Good. So then what we're going to do is we're going to allocate numbers to all of the steps in the paths. These numbers are going to be between 1 and 3. This is going to indicate where the number comes in the Young tableau. Okay, so whenever we see a marked level step, we're now going to allocate the number 1 to it. And then from right to left, we're going to number the first down step, and then the next down step that comes after this level step, we're going to number 2 and 3. Okay, so over here, 1, and then the next down step is there, and then the next down step is there, and then similarly repeating the process. Then we're going to follow some numbering process which has been outlined in the bijection between these Young tableau of height less than or equal to 3 and Motzkin paths. So this process, essentially, you recursively repeat this process from left to right. If you have a level step at the start of the path, you number it 1. If you have an up step at the start of the path, then what you do is you look for the next non-up step, okay? And if the next non-up step is a down step, then it becomes 2. If the next non-up step is a flat step, the flat step becomes 2, and then the next down step after that becomes 3, okay? So maybe it is helpful to look at 1 or 2. So we have 1 over here, the first up step. We look for the first non-up step. 2, we mark that 2. Then we repeat the marking on the path that remains. So we have an up step on what remains. We go for the next non-up step, which happens to be a flat step. We mark it 2, and then we look for the next non-marked down step. So this one is marked. So we continue for a while until we get to the next non-marked one, and that gets labeled 3. And we repeat this process until everything in the path is marked. Okay? And then once we have our full numbering, what we do is we append a 1 onto the start, and then going from left to right, we write the numbers 1, 2, 3, 4, 5, 6, and so on. We write them then in our shifted Young tableau. Okay. So that is the entire procedure for busy going from a moving boundary path with those specific requirements to a shifted Young tableau. And now, in a very hand-wavy way, I will say you can go back. You follow the reverse procedure outlined by you in the bijection between Motzkin paths and shifted Young tableau of height less than or equal to 3 to get a path. And then what you do is you identify the flat steps that are coming immediately after a sequence of up steps. And then you use those as number 2s. Or they are number 2s already, sorry. You go to the first up step at the bottom of some sequence of up steps just before that step. You mark that. And then you mark the first down step afterwards. And this will give you sequences of 1, 2, 3, which then correspond to your original marked 1, 2, 3s that are there, okay? And then using that procedure and then doing the reverse procedure for busy building up the 1, 2, 3s, you then end up busy getting back to the moving boundary part. Okay, so then we can take a look and see what happens with these moving boundary situations, because as I said previously, we have push-down automata that are busy encoding these one-dimensional things, but we would be interested to understand a little bit the underlying structure of these two-dimensional things, which seem to have nice generating functions, but not necessarily nice encodings. And we can do some searches to try to find interesting sequences, interesting relationships on, for example, the moving boundary in 2 dimensions. And so this is ongoing to try and figure out relationships, maybe figure out some underlying structure and nature of generating functions in these cases. Okay, so just to finish off, some future directions. Hopefully people here are interested in working on these types of things relating to walks and patterns in walks in the quarter plane. So just studying walks in the quarter plane was quite an extreme effort of many members of this community, and so hopefully people will take methods and try to apply them to patterns in walks in the quarter plane. So the first one, and it's a little bit ambitious, is that hopefully at some point somebody finds a proof from the book, a really simple, nice explanation for Creverous enumeration. The next one, as I mentioned previously, is there's no real way to classify what's actually happening in the generating functions when we're busy avoiding patterns in walks in the quarter plane. So determining some sort of classification, even just a really small one. So then also, perhaps studying walks in the quarter plane can be done by busy using things like these two-way reversal bounded counter machines. So finding ones that can be encoded by these two-way reversal bounded counter machines and somehow studying those patterns via that. Or else to try and adapt some sort of kernel method to try and figure out a functional equation for pattern avoidance or studying patterns in walks in the quarter plane, even just a really nice, simple example. And then the other thing, which I'm quite interested in finding out if this is even possible, is to try and find, so we have this language and this type of automaton for definite generating functions. And so in automata theory and in formal language theory, you have these results like the pumping lemma, which then tell you when a language is not part of a set of languages. So somehow busy being able to use these languages for definite languages, or automata the language, or grammar, somehow being able to develop results which then tell you that it's not a definite language would be quite interesting. Good. And then maybe just to, well, thank you very much, but I have one additional little thing to say. And that is, so, well, I'm originally from South Africa, and in South Africa, I saw so many mathematicians who were extremely talented and had really a lot of potential. And then I came to international research sphere, and I was a bit like, where are they? And so the thing that I realized was that ultimately there's also a lack of opportunity that exists, in Africa at least. So there's the opportunity, lack of opportunity is often funding. You don't have funding to travel to conferences and access to people, other researchers, you're geographically isolated. And so basically I thought, because we had a combinatorial enumeration event, in January, some of us from the analysis of algorithms community got together and made a summer school in South Africa for enumerative combinatorics with applications to computer science. But I wanted to try and encourage all of you to get involved in trying to bring mathematics to developing countries. I mean, there are billions of people who are not, well, I mean, to support mathematics in developing countries, because they are really talented, enthusiastic people who just don't have access to the opportunity necessarily. And so there are institutes like SIMPA, French, so France is really behind this. SIMPA, you can apply for funding for schools. And many of the students at our school had never actually been to a school or a conference before. They just didn't have funding for it. SIMPA funds everything. And there's also the African Institute for Mathematical Sciences that you can volunteer to give a course, a 3-week course often really nice venues. You have access to, like in South Africa, the one is opposite a surfing beach. So really, it's like you get to interact with very talented, enthusiastic students. You get to go surfing. There's no downside. So I would really like to encourage all of you, if you do have time or passion or resources, to please get involved in busy providing opportunities to talented people who don't necessarily have access to these opportunities. So thank you very much.
Thank you. Are there questions?
Hello, thank you for your talk. I just had one small question. You showed how to derive a functional equation for counting words in one stack, in an automaton with one stack. Yeah. What prevents you to do the same with two stacks?
So two stacks. The thing is, two stacks becomes very hard because they're equivalent to Turing machines. And then counting becomes a bit, it's not really clear how to count. So especially even with the two-way machines. So maybe this is also something I'm thinking of. So if anybody has an answer, please tell me. But with two-way machines, so two-way machines, if you're not having a stack, if it's just a normal two-way machine, being able to move left and right can really mess with trying to set up a generating function from a two-way machine, when a two-way machine is actually equivalent to a deterministic finite automaton. So technically, a two-way machine should encode a rational generating function, but ultimately, trying to get a rational generating function out of a two-way machine is very hard because of this back and forth movement. And so the reason that the push-down automaton with one stack sort of works is because well, methods are developed, although they are a bit difficult to implement at times, but I would say with two stacks it might be very hard.
I'm not talking about something about obtaining an explicit generating function, just a functional equation, maybe with catalytic variables.
I mean, maybe it's possible, but I would, yeah, maybe it's possible.
Okay, thank you.
Questions? So I have one question, maybe you said it, but I missed it. So a definite language, you mean a language whose generating function is definite?
Yeah.
So is there a notion of definite language? Because in the algebraic case, I guess the pumping lemma is not really for algebraic, but for like context-free.
Yeah.
So would there be an equivalent of context-free for the definite, like in purely language theoretic wording? Yeah, so
there's this sort of adapted shuffle of context-free languages by Mani and Mike Zabrocki, which encapsulates definite languages or languages which give definite generating function. You might have to do a little bit of an adaptation to it slightly, so it's not necessarily all definite generating functions, but I mean, it exists. I mean, you don't get all algebraic generating functions out of context-free, so if some sort of pumping lemma could be developed for that, I mean, there are pumping lemmas for shuffles of languages. So perhaps some sort of pumping lemma could be used to then classify some generating functions.
Thank you. Are there other questions? Well, thank you again.